Okay, we can start this unit. This is unit number 4. So in this unit, what we are going to see is the manufacturing consideration in design and design of shaft, keys, and coupling. Basically, in previous syllabus, there was 2 chapters. One chapter was as a manufacturing considerations in design, and second one was design of shaft, keys, and couplings. So in this case, what we are going to start, if you are going to see the syllabus, then syllabus is divided into 2 parts. There are 2 separate paragraphs you can see here. One is design consideration for casting, design consideration for forging, design consideration for machining parts, design of for manufacturing and assembly. This is one part, which is theoretical one, and second one is that design of shafts. Then it includes shaft material, design of solid and hollow shafts on strength basis. Basically, we are going to see design of shaft on 2 criteria. One is maximum principal stress theory, and second one is maximum shear stress theory. Also, we are going to see the design of shaft based on torsional rigidity. Then ASME code for the shaft of design of shaft, and design of square and flat keys. Square and flat. That is the only these 2 keys we are going to see how to design. In splined shaft, only we are going to see introductory part of that splined shaft, and then types of coupling we are going to see. Out of that, muff and rigid coupling. So we are going to see all this part in this unit. Now, if we are going to see the next slide, then we are going to see first of all what will be the design considerations. First part is design considerations in casting. When we are going to see the design consideration, what we are going to, what you mean that design considerations? Design considerations means what? Can anybody of you give me answer? What do you mean by design considerations? You can text. What do you mean by design considerations? Can you hear me? What do you mean by design considerations? Yes, somebody has given answer, Deshpande. Some assumptions which can be made while designing. Okay. Some assumptions which we are going to make while the designing. Yes. Okay. These are some considerations or assumptions, or you can say thumb rules. Okay. That we have to make at the time of designing of that part. Okay. So when we are going to design any part, at that time, what we are going to consider, okay, that that part should possess, that we are going to say as a design considerations. Okay, that is nothing but based on some natural principles. What we are going to assume or what we are going to consider that part should possess, that part should have, that is known as a considerations. And if you are going to do it at the time of designing, then we are going to say it as a design considerations. Now, design consideration is very vague term, whereas if you are going to do design for the manufacturing, okay, manufacturing includes casting, forging, machining, okay, these are the manufacturing process. So when we are going to consider that our part will get manufactured after designing, what we are going to do is that we are going to manufacture that part. Once you design, once you calculate all the strengths and dimensions, you are going to prepare a drawing, and that drawing will be given to the manufacturing. So that part has to be manufactured. Then designer is going to decide which process can be implemented for the manufacturing. Whether that part should be manufactured by casting, or it should be manufactured by forging, or it should be manufactured by machining. So all these things the designer is going to decide. And while deciding all these things, the designer is going to consider that some logical things in that design. Okay. So we have divided these considerations in design consideration in casting. That is when we are going to manufacture that part by casting. Then what that design should include, what it should possess, that we are going to see. Okay, later on we'll see design considerations in forging, and then afterwards design considerations in machining. Okay, so first part, what you have to consider at when we are going to design any component for the casting, that always keep the stressed area of the part in compression. That is maximum stressed area which we are going to consider, that is kept in compression. Now here you can see the two diagrams. One diagram is showing that one shaft is supported by means of this support. Okay, this we can consider as a support. So this is supportive bearing, and this shaft is in this hole. Shaft is supported by means of, here I can take pen. So in this case, when we are going to consider that the shaft to this hole is supported by means of this bearing. So when we are going to consider that this bearing is manufactured by means of casting, then there are two separate methods. One, that we can hang that shaft. Okay, that means the gravitational force or its weight will act in downward direction. Here also, that no doubt that shaft is going to act weight in downward direction. But if suppose we are going to create the compressive stresses in casting, because you know that gray cast iron is strong in taking compressive stress rather than the tensile stress, right? Because basically cast iron is of brittle nature. That's why our part which we are going to manufacture, we have to consider that it will be of brittle nature. So we have to avoid maximum fluctuations in that part, that fluctuation of loading, okay, fluctuating stress, that also should be avoided, and that part should undergo to the compression instead of having tension, instead of creating tension in that part. Okay, so this we have to consider at the time of designer, because designer is going to decide how to give the support to that shaft, whether it is hanging type or it will be supportive type. Okay. Only thing is that designer has changed the orientation by means of the shaft is supported. This is the first consideration. Then second consideration, round all the external corners. And here you can see the example that the part which is manufactured by means of casting, here the sharp corner is provided. You have to avoid these sharp corners. Instead of that, if we use some radius, if we avoid that corner, sharp corner, then it will be better. Because at the time of casting, you know that when material is poured, at that time the sharp corners will not be maintained. Okay, in case of that manufacturing process, so it should be avoided. Next thing, wherever possible, the section thickness throughout should be held as uniform, as is compatible with the overall design considerations. That means as the part is supportive, as where with the design is supportive, then we have to avoid sudden changes, okay, in the area. We have to keep it as a gradual decreasing, because this manufacturing process will allow to flow that molten metal gradually. Okay, and when it will get cool, then at that time stress concentration will not be occurring that. Okay, so when we are going to consider that this part has to be manufactured by means of casting, here in first A diagram you can see here that the corners are sharp. Okay, 90-degree corners are provided. Whereas in B, the corners have rounded. Whereas in C, that same length of that part is achieved by means of decreasing that area gradually. Okay, by means of one concave shape. Whereas in the fourth, that is D diagram, that has gradually changed with the straight line. Okay, so which is the best. So this consideration we have to consider at the time of designing of any component which will get manufactured by means of this casting. Next, fourth is that avoid very thin sections, means uh, very thin part which will get manufactured by means of casting will create much more problems. Okay, so these thin parts we have to avoid to manufacture by means of this casting method. We can go for the other type of methods by means of which it will get manufactured. Okay. And fourth, avoid concentration of metal at the junction. Here you can see these are the four ways. Okay, and it will get manufactured by means of casting. And at this junction of these four ways, this material has get concentrated. Okay, where we may have the possibility of blowholes or cavity. Okay, so we have to avoid at the time of designing only, we can avoid such type of concentration of material. What we can do here, if the design, because we are designers and we can do that, if we provide hole here which will be hollow. Okay, then concentration of material has avoided. In this case, if these four ways may get, the dimension may get changed. Getting, so that dimensions has to be changed. But we have to consider that the concentration of this molten metal or metal should not be there in any component which we are going to design. Okay. Then next, these are the five considerations which we are going to consider at the time of manufacture any part by means of casting. Next, we are going to see design considerations of forging. So suppose we decide that part has to be manufactured by means of forging, then again there are some rules that by means of which manufacturing process which part will get manufactured. Okay, how we are going for the manufacturing of any component, that is decided by means of one thumb rule. Okay, so forging where the stress handling is more, whereas we can say that fluctuating stresses are more. That parts are normally forged. Okay, for example, crankshaft, then camshaft, okay, of engine. These are the parts which are manufactured by means of forging. Now, what consideration we have to do at the time of designing any part which will get manufactured by means of forging? First of all, while designing forging, then advantages should be taken of the direction of fiber lines. Now here you can see when we are going to manufacture same part by means of three different methods. One is by casting, okay, that is by means of casting method. Whereas second part, this same part is manufactured by means of machining, okay, and same part is manufactured by means of forging. Then what happens in case of casting? That grain size will be evenly distributed. Okay, while the that molten metal is going to be cool at that time, the martensite, then all that you might have learned in metallurgy. Okay, then ferrite, martensite, all that part will get concentrated in that material, and that grain size is decided by means of what is the cooling rate. Okay, and as per that composition of that material and alloy of that material, that grain size will be generated. But in that case, no line will be manufactured, no line will be observed. In that case, simply that part will get cool as it is, and hence the crystallization is more. That is nothing but it will be, we cannot say perfect crystallized, but that molecules will get freezed over there only. Okay. Whereas if the same part is manufactured by means of machining, then due to the machining, as you are going to shear out some material, what the machining means? Machining means you are going to remove the unwanted material from a job, any what we can say rough job. And this unwanted material which you are going to remove, while removing it, you are going to shear out that material, which is not required. And while shearing, that stresses will be get induced, shear stresses will be get induced. Okay, and hence the lines are produced by means of that shear lines, we can say. Okay, and this grain structure is become as a lines. Whereas if you are going to forge that component, then the forging force, that is nothing but you are going to create compressive force in that. And later on, you are going to remove that compressive force when it will get that shape, required shape. Okay. In that case, the forging line or that stress lines will be created. Okay. Grains will not be concentrated as there in casting. Okay. It will have this line type of grains, which will get cool in case of this uh, forging type of manufacturing. Okay. So one should get advantage of this. While we are going to force that component, then it will be more stronger in case of tensile load. Okay, if the force is applied in this direction, like this, then it will be sustained. Okay, by means of these lines. So one can consider that thing while designing of this manufacturing process, or while we are going to select this manufacturing process at the time of designing only. So parts which are undergoing to the tensile load, okay, fluctuating tensile load, or we can say bending also. Yes. So while it will undergo to the bending because vertically and is supported by means of bearings, suppose here. Same part. I am going to give example of same part. Okay. If it is supported here, and here, and if undergoes to the this vertical load, then it will undergo to the bending. But what the bending is, basically it is tensile and compressive, right? So tensile stress will be sustained, compressive stress also will get sustained. Okay. So these advantages we have to take at the time of designing only. Then in case of next slide, second consideration is that the forged component should be provided with the adequate draft. Now, what do you mean by draft? You might have learned draft is nothing but the angle which is provided to the component, right? So when we are going to provide that angle is normally known as a draft angle. You might have studied it in manufacturing process, GMT. So same part is there, which is manufactured by means of forging. But what advantage we are going to get here in the second modified part, that the forging die will be easily manufactured. Okay, whereas these sharp lines, straight lines, it will be very difficult. That die cost and all manufacturing cost will get increased. So as far as possible, we have to provide some angle. No doubt that tolerance will be provided. But to maintain that tolerance, what we have to do is that when we are going to use the forging as a manufacturing process, the component should be provided with the draft angle, okay, that adequate draft angle, so that the strength will also get increased, as well as the function of that component will be obtained. That functioning will be done easily. Okay. Next. Parting, if you are going to see the part which is manufactured by means of forging, then you will have one forging die and forging hammer, right? So in case of forging die, some part will get shaped by means of forging die, on which the forging hammer is applied. Okay, that also get same shape or the shape as per provided by means of that die. So we are going to take this typical example. In this example, what we are going to do is that we are going to manufacture this job. Okay. So in this job, this is die and that hammer, blow hammer will be applied on this die. So one line will be created, which is known as a parting line. Okay. And this parting line that divides the forging into two halls, that is two parts. Basically, it is single component. It is not assembled by means of two components, but it is a single part. Okay, but one sharp line is created due to the that die and hammer. Okay, so we have to keep that the minimum depth to which the steel must flow to feel the die impression. That means in die, maximum flow should be there with the hammer, not with the die. Okay, so that the flow of that material or steel components, we can say. Basically, forging is applied for the steel components as well as for the uh, bronze and all other non-magnetic components also. Okay, but this forging is widely used for the steel. Very, very, very rarely it is used for the non-ferrous material. It is widely used for the ferrous material only. Okay, so while this material will get flow, because you know that in case of forging, what we are going to do? You are going to heat that component job at certain temperature. Okay, near about 720 degrees Celsius, which is the recrystallization temperature of that ferrous material. Okay, I'm not sure about it. Okay, I'm not exactly telling you what will be the temperature that you can find in metallurgy book, but uh, that temperature is near about 720 degrees Celsius, where that part will get heated as a red hot, and then afterwards flow of that material will be take place, and we are going to apply the hammer, that is forging is done, and hence while the material will get flow, that should be flow more in the hammer and less in the die. Okay? That care we have to take while designing of that component. Okay. And next, no doubt that this care has to be taken at the time of designing of die also. Okay, of that uh, die and hammer, while designing that die and hammer for the manufacturing. At that time also we have to take this care. But our component should be in such a way that the parting line, in that parting line, small material should get flow in die and maximum material should get flow in the hammer. The forging should be provided with the adequate fillet and corner radius. That means here also we have to avoid that sharp corners. Okay, that fillet radius has to be provided for that. Then thin section and rib should be avoided for the forged component. Here, in case of this forged component or component which will get manufactured by means of forging, we have to avoid ribs as well as the thin shape. Okay, because in that case it may damage that rib, or that thin shape may get damaged at the time of forging, and that's why that part may get rejected. Total part may get rejected. That's why it should be avoided, and The designer has to be take care of this. Next is design considerations of machining parts. When the part is manufactured by means of machining, then what consideration, what care we have to take, that we will see. Up till now, do you have any question, query? If you have, you can ask. Hello? Is there any query? Hello? Can anybody answer? Do you have any query? Yeah, sir has given no, sir. Okay. So design considerations when part is manufactured by means of machining. First is that avoid machining. Okay. So as far as possible, we have to avoid this machining process. Why? Because machining operation increase the cost of that component. Definitely, because we have to remove that unwanted material, then we have to check the surface quality, and we have to use tools, we have to use machine tools, that is CNC, VMC, lathe machine, shaping machine, drilling machine, all that machines that will increase the cost of that component. As far as possible, that component should be manufactured with the help of about two methods. Okay. So first consideration, as far as possible, avoid machining. But you know that it is very difficult to avoid the machining of any component. There are very few components which will get manufactured and is not required any machining on that component. Very, very few. Okay. Second is that uh, specify the liberal tolerance, because these materials or that components which are getting manufactured by means of machining, depending upon the machining condition, that tolerance will get maintained. Okay, so we have to provide as far as liberal that tolerance. Okay, uh, on that component. Okay, so in this case also avoid sharp corners, because sharp corners will be create stress concentration. Okay, so sharp corners has to be avoided. Then use stock dimensions. Okay, raw material like bar are available in the standard size, because when we are going to create or when we are going to design any component, then as we have seen that if the component size is 12.7 millimeter, then we are going to select it as a 13 or 14 or 15 millimeter, right? So as far as possible, we are going to make it as a standardized, because to maintain the 12.7 millimeter, it requires what critical machining. Okay, very sharp tolerance is provided in that. But roughly, if you are going to make it as a 15, and if you are going to give tolerance as a plus minus 0.01, then it will be achieved easily. Whereas this part will also get will have the same strength or more strength. Okay, so it will not fail at the time of application. Then design rigid parts, as already I have mentioned that if the dimension is coming as a 12.7, we have to take it as a 50. It will become rigid. Okay, so likewise we have to design when we are going to manufacture that part by means of machining. Okay, then avoid shoulders, that shoulder is nothing but now here this diagram. Okay, we have to avoid as far as shoulder means where we are going to apply load and which will be in hanging position. Okay, that type of design we have to avoid. Okay, and undercut shoulders, that is nothing but uh, this type of component where it will be subjected to the bending load and it is undercut. If you are going to manufacture it with the help of machining, then we have to use boring as an operation, right? We have to bore this much part. We have to remove this material. Okay, and in this case, this is called as shoulder hanging. Okay, so we have to avoid such type of design, undercut shoulders. Okay, and undercuts, any undercut that is which is creating the boring operation. Okay, so it requires that specific tools. Okay, and which will increase the cost of that machine. That boring bar and boring tools, this separate tooling is required for that, which will increase the cost. Okay, then avoid hard materials. So if you are going to manufacture any component with the help of machining, then that material which you are going to use, that should be considerably soft, because hard material requires more amount of tooling. If that tool which you are going to use, it requires more harder, right? And definitely that cost will get increased. That's why we have to avoid the hard materials if the part is manufactured by means of machining. Next is that design for the manufacturing and assembly. It is known as DFMA, design for manufacturing and assembly. What consideration we have to do while we are going to design any component, what manufacturing considerations and assembly type of considerations. That is, two separate parts are manufactured in two separate companies, countries, okay, at two end of the world, and it will get assembled somewhere and will be utilized for that particular component. For example, as we are going to see the Maruti car, basically engine of that car is coming from the what we call Korea or Japan, because it is collaborative with the Maruti and Suzuki. That's why engine which is provided to the Maruti is coming from the separate countries and it will get assembled here. So that consideration in the design only we have to do when that part will get assembled together. Okay. As far as possible, we have to reduce the separate parts, that is part counts. Okay. Then use modular design, that is nothing but use standard material, okay, being assembled at one time. That is modular. It is called as modular design. When the number of parts are assembled at a time, okay, and also simplifies the final assembly. Assembly should be simple. Okay. Then optimize part handling. Much more parts should not be there. We have to take screw, we have to take nut, we have to take panel, we have to take all these things. It will require handling of so many parts. Okay, so we have to design a component in such a way that it will be optimum handling of that component. Okay, so many times, that is you might have seen the manufacturing line, engine manufacturing or engine assembly line or car body manufacturing line. In that case, at every station, separate operation is created. So one part is handled too many times. So our design should be in such a way that the minimum possible handling of that component should be there. Okay, it is called as optimization. If it is not possible, we cannot avoid it, then we can keep as it is. But we have to, or we have to try for reducing the handling of that component. Next is assembly in the open assembly. That is, while we are going to assemble that part, it should be open assembly. Okay, that assembly operation should be created out in the clear view. That is, it will be under the roof. Okay, it should not be under a compart or any closed compart. Okay, compartment we can say. It should be open. Okay, while we are going to assemble. For example, we can take example of uh, car manufacturing, car body manufacturing, especially. Okay, it is not done in compartment, so it doesn't require compartment basically. That's why when we are going to design any component, but if you take the same example, when the we are going to paint that component, painting is done. That painting is done in closed compartment. Okay, so that type of operation, basically it is an operation which we cannot avoid actually. But as far as possible, when we are doing assembly, it should be in open space. Okay. Next thing is that while we are going to assemble any component, we should not fight against the gravity. We have to take advantage of gravity so that the parts which are applying their own weight in downward direction, always every part on earth is applying his weight in downward direction. So we have to take advantage of that gravity. We should not fight against that gravity. That means we have to lift that part and then afterwards we have to assemble it, and we have to use nut and bolts for fastening that. Instead of that, from above, if the assembly is coming and if it is fitted, that will be better. It requires less energy. So we should not fight against the gravity. Okay. The design for the part identifier. Each part should be identified separately. We should not get that worker should not get confused in different parts. That part should not be identical. Okay, they are having separate identity. Then, as far as possible, eliminate the fasteners. Fastener means nut and bolt. Okay, rivet. So rivet is the permanent fastener, whereas nut and bolt is temporary fastener. But as far as possible, it is not possible to completely avoid the fasteners. But as far as possible, we have to eliminate that fasteners. Okay. Then our assembly should be simple one. It should not be complicated. While we are going to assemble it, it should be simple as far as possible. Try to simplify our component. Okay. Then reduce, simplify, and optimize. Our assembly should be simple. Then optimize. Okay. And also you have to simplify with the manufacturing process. Okay. These are some considerations which are done at the time of manufacturing and assembly. So any query related to this, so that we can go to the next part of the chapter. Yes, do you have any query? If not, we will go to the next part of the chapter, that is design of shaft, keys, and couplings. How we will take first shaft, how to design the shaft. Then afterwards we will see key. Okay. In this, we have to design only square and rectangular keys. And then afterward couplings, we are going to see the couplings. In that again, we are going to see only two couplings. Okay. So can anybody of you tell me what do you mean by shaft? Hello? Let me know what do you mean by shaft? Can you read it? The term transmission shaft usually refers to a rotating machine element. Shaft is usually rotating. Okay. Circular in cross section. Normally. Okay. Shaft is in circular cross section, which supports transmitting elements. On that shaft, we are going to assemble transmitting elements like gears, pulleys, okay, sprockets, and power is transmitted. So the element which is supporting to the transmitting elements, that is pulleys, gear, sprocket, we have seen that in case of belt drive we have to use pulleys. Then in case of gear drive we have to use gears. Then in case of chain drive we have to use sprocket, okay, to transmit the power from one place to another place. So who is going to support these elements? That supportive part is known as a shaft. Okay, so we have to design this shaft. Now, when we are going to design this shaft, first of all, we'll say what are the different types of that shaft. Now, shafts are broadly classified in five parts, five types. Out of that, one is known as axle. The axle is nothing but the shaft which supports to the rotating elements like wheels. Uh, when we are going to use word axle, it means that uh, that rotating elements are wheels. For example, we are going to say uh, trolley axle, axle which is supporting to the wheels of that trolley. Whereas for the cars, when the power is transmitted from engine to wheel, the element which is transmitting is basically shaft, but it is known as a named as a axle. Okay, it is supported by means of wheels. It is known as axle. Second is spindle. This word you have heard in case of lathe machine. So when we are going to see that shaft as a spindle, when it is short rotating shaft, length is very short. At that time, we are going to call it as a spindle. Okay. Then counter shaft. This counter shaft is nothing but the main shaft is there, and in supportive with that main shaft, if we are going to use another shaft, that another shaft is known as counter shaft. Okay. So we are going to say it as a counter shaft. Then next is jack shaft. It is actually auxiliary shaft. Okay, that is hello. Sorry for the interruption. When that shaft is used, two different shafts are used to transmit the power. At that time, in between that, if the supportive shaft is provided, that shaft is known as jack shaft. Jack is nothing but basically uh, which supports screw jack. Have you heard this word? The jack which we are going to use for the disassembling of wheels of any automobile, that you are going to call as a jack. Okay, normally known as a screw jack, because uh, the shaft which is used in that is having threads on that. So it is known as screw, and jack is nothing but support. Okay, so the shaft which is supporting two different main shafts, it is known as a jack shaft. Then last is line shaft. Line shaft is nothing but if you are going to use number of machines which are running on the same shaft. That is gang drive and individual drive. You might have heard this word. That gang drive is nothing but on single shaft if you are operating different machines. It is called as gang drive. Okay. And if you are going to use individual machinery or motor or prime mover, It is known as individual drive. Okay, so that shaft which is used in gang drive, it is known as a line shaft. Okay, two different or many machineries are operated by means of that shaft. It is known as a line shaft. Okay, any question? Question related to this? Hello? If not, we'll go further. Next, the material which is used for the shaft. How that material should be. Okay. And what are the standard ASME standards are there for the material or Indian standards which are provided to that material. So while we are going to select material for the shaft, at that time it should have the high strength that normally hardened bars are used for the shaft. Okay. It should have good machinability because the shaft is of step shaft basically. That is nothing but we are going to use different diameters on that shaft. Okay, so it is called a stepped shaft. Then we have to avoid as far as possible the notches which are created on that shaft, but it should be less sensitive to the notch, the material which we are going to select. Okay, that means tough material we have to use. Then it should be good heat treatment. That means it should be respond to the heat treatment because after manufacturing we have to go for the heat treatment for that shaft. We have to harden the case of that shaft so that we can avoid the wear and tear of that shaft. Okay. Then it should be high wear resistant. Okay. The material which you are going to select for the shaft. Now, which materials are coming under the category of all above this, which we have seen five qualities, which may get induced in that. So normally, in that case, 40C8, that means 0.08% carbon is provided in that. Then 45C8, 50C4, and 50C12. These are the standard materials, okay, as per the Indian standard. That these are the standard materials which are normally recommended for the shaft, where that tensile strength and yield strength is provided in this table for that respective material. If you are going to take example as a 40C8, then it has a ultimate tensile strength as a 560 to 670 megapascal. Okay. Then if you are going to see yield strength, it has a yield strength of 320 megapascal. Okay. So these are the this table will provide us the strength as well as name of that material which we can use for the manufacturing of shaft. Okay. Now how we can design this shaft. So before going to this design, can we take a short break of 5 minutes? Hello? Hello? Okay. We'll take break of 5 minutes and later on again we'll reassemble for the lecture. Okay. With the same link you can join. Can you listen me? Hello? Hello?
Yes, sir.
Okay. So, thank you. We'll proceed further. For designing of shaft, we are going to see. Next is that we are going to design this shaft based on the maximum principal stress theory and maximum shear stress theory. Based on these two, we are going to design the shaft. Okay. So while we are going to design it based on maximum principal stress theory, we have to consider that the normal stresses in that shaft are exceeding, and due to which the failure is occurring. So basically, shaft we are going to consider that it will undergo to the two stresses, that is torsional stress and bending stress. Why? Because when we are going to consider any shaft, if we consider that this is shaft and if it is supporting to gear or any pulley, consider that this is supported by means of this pulley is supported or gear is supported by means of shaft which is rotating. Then in this case, we are going to provide bearings to both sides, which will sustain the load which is coming on vertical as well as horizontal direction. Okay. So when we are going to consider it that due to this own weight of this pulley and whatever may be the force which is acting, because of that, the bending will occur of this shaft. So bending stress will be get generated, right? And as we are going to rotate this pulley, okay, suppose this pulley is rotating in this direction, then as if it is going to rotate, then torsional stresses will also get generated. So these are the two basic stresses which will get induced in the shaft. That is, one is bending, and second one is torsional. So torsional and bending stress will get induced in this shaft. Hello. So torsional stress and bending stress. Because of that two stresses, this maximum shear and maximum principal stress. These two stresses will get induced. So first of all, we will see that if the shaft undergoes to the maximum principal stress, how the failure is going to occur. So it is known as maximum principal stress theory. So maximum principal stress, let us consider that the tau is nothing but the shear stress which will induced due to the twisting or torsional movement in that shaft. Okay. And sigma B is the bending stress. Normally it is tensile or compressive, which we are knowing as a principal stress. Okay. So if this tensile or compressive stress get exceed, then failure is going to occur. That this theory is going to suggest, principal stress theory. So sigma B is considered as a bending stress, that is tensile or compressive, induced in that shaft. Now we know that this sigma B max is given by means of 1/2 sigma B plus 1/2 sigma B square, that is bending stress square, plus 4 times tau square. This is the formulae which we have derived in unit number 1. Okay, where we have seen that what is the maximum principal stress theory. Okay, so half of the bending stress plus half of the total or equivalent stress that we are going to see. So while we are going to see this formulae, that maximum bending or principal stress is given by 1/2 of its one principal stress plus 1/2 principal stress plus torsional stress. Okay. So this is basic formula. Now our job is that we have to calculate this bending stress plus, and then we have to calculate this shear stress. Then afterwards we will put value of this bending and shear stress so that we can get the maximum principal stress, that is bending, maximum bending stress. Okay, either it is tensile or compressive. So let us consider that in case of bending, we are going to use this equation. M by is equal to sigma B by Y is equal to F by E. Okay. So this equation, in this equation where M is the bending moment which we are going to calculate from the support and applied load. I is nothing but the moment of inertia of cross section of that shaft. Here we are going to use circular shape. That's why pi by what 64 d raised to 4. That will be the moment of area moment of inertia. Okay. Then sigma b is the bending stress, where sigma b is used is the bending stress, and y is the distance from the neutral axis of outermost fiber, which we'll call it as a r or d by 2, right? When we are going to put values of I, y, we'll get this equation as m is equal to pi by 32 sigma b into dq. In this equation, m by I is equal to sigma b by y. In this equation, we are going to put value of I as well as value of y. Okay, I is nothing but pi by 64 d raised to 4 and y is d by 2. If you are going to put these values, then we are going to get equation as m is equal to pi by 32 sigma b into dq. Likewise, if we are going to see it for the twisting moment, there is nothing but the torque. Okay, and due to torque, if the shear stress tau is generated, in this case we are going to write equation as T by J, where J is the polar moment of inertia, T is the twisting moment or torque which is applied on the shaft, is equal to tau is the shear stress divided by R. R is nothing but the d by 2. Okay, that is distance of neutral axis from the outermost fiber, outermost layer. Okay, so in this equation, J is put as a pi by 32 d raised to 4 and R is put as a d by 2. If we are going to put these values of J and R in this equation can be rewrite in terms of T as a T is equal to pi by 16 tau dq. Now this T and this M, which will give us values of sigma b and tau. So these values we have to put in the equation which we have derived for the maximum bending stress. Okay, that is the maximum principal stress. Okay, so if you are going to put value of that sigma b and tau in terms of bending moment and torque, we'll get equation as sigma b max is equal to half. Here sigma b was there, that is 32 m divided by pi dq plus 1 half under root sigma b square, that is 32 m divided by pi dq. Okay, plus 4 of tau square. Tau is nothing but 16t divided by pi dq. Okay, so this equation we can write by taking this 32 divided by pi d cube as a common. Okay. Also, we can take this half as a common when we are going to take outside, but we'll keep this half inside the bracket. Okay. So we can get this equation as half of m, this m, because we are going to take 32 divided by pi d cube as a common. Okay. Half in total from this also and this also we are going to take common. Later on, we will multiply this half with the 32. It will become 16. Okay. So half m, this total, this is remaining m, plus this m, that is m square, plus this t, because we are going to take this 32 divided by d pi d cube as a common. Okay, so it will become 32 divided by pi d cube into bracket half of m plus under root m square plus t square, right? So when we are going to put this value and this 32 divided by pi d cube to the other side, this equation will become as a pi by 32 pi by 32 d cube sigma b as it is equal to half of m plus under root m square plus t square. Now this term has been separate out, that is half of m plus m square under root m square plus t square, because this expression is known as equivalent bending moment, okay, which we have calculated and is denoted by m suffix e, sigma e. Okay, so this equivalent bending moment, that is while we are going to consider the principal stress as a sigma b. Okay, so equivalent bending moment may be defined as the moment which when acts along the and produce same tensile or compressive stress, that is because of the shear and because of the bending, this equivalent stress is generated. Okay, and it will create the same amount of tensile or compressive stress as in case of actual bending. Okay, so it is going to regulate the limiting value of sigma b. Okay, and this sigma b, that is the maximum principal stress that we are going to take for that material, and we are going to calculate value of d, because here we have to calculate dimension, that is the diameter of that shaft. Okay, and that is calculated as a d. Any question? Hello? Do you have any question? Hello? Yes or no? Anybody else? I understood it, or should I repeat it? Yes, we'll go further. Same way, if we are going to calculate the stress that is maximum shear stress theory. Okay, so in this case we'll use the maximum shear stress theory. According to the maximum shear stress theory, this tau max is given by, that is the maximum shear stress, is given by half of the bending stress square plus 4 shear stress square. Now all these equations we have calculated in first chapter by means of Mohr's circle, if you are remembering. Okay, with the help of Mohr's circle we have calculated this equation, shear stress equation. Okay, now this shear stress equation we can rewrite in terms where we can put value of the sigma b, okay, and tau, because already we have calculated this value of sigma b and tau. from this equation. I'll take this equation and this equation. Okay. So from these two equations, this sigma b will take from this equation and value of tau will take from this equation. Can you just suggest here I will insert this equation. Okay. This equation how we can modify for the sigma b. I want to rewrite this equation in terms of sigma b. What I should write? Sigma b is equal to this 32 will go to this side, d cube will go to this side, pi will also go to this side. So what I can write here, 32 m divided by yes, pi into d cube. Are you listening me? Hello?
Yes, sir.
Okay. So please help me if I'm doing anything wrong. Can we write this sigma b? Now already you know that how we calculated this m. M is equal to pi by 32. हे कशावरून काढलं m by I is equal to f by y is equal to e by r. Okay. So we have calculated it. F means sigma b by y. From that y we have put as a d by 2 and I we have put as a pi by 64 d raised to 4. Okay. Now this equation which has modified from this m. Okay. And here again we will modify this equation. Okay. Here. So we'll write this equation in terms of tau. So here tau is equal to what we can write t into 16, that is 16t divided by pi d cube, pi into d cube, right? Now these two values we have to put in this equation. Okay, value of sigma b and tau we have to put in this equation and we'll get the final equation. Okay, so what we can write? We'll get this equation. Okay, so this equation which we have derived from this maximum shear stress theory by putting value of sigma b and tau. So we have got this 1/2 as it is. Value of sigma b is 32 m divided by pi d cube bracket square plus 4 into 16t divided by pi d cube, that is the value of tau bracket square. Okay, we'll take this 16 divided by pi d cube as a common. Pi d cube is here, pi d cube is here, 16 is here, then 32 is here. Okay, so we are going to take it as a common. So when we are going to take, basically we are going to take this 32 as a common. Okay, so we'll get this equation as 16 divided by pi d cube into bracket m square, that is bending moment square, plus t square, that is torque square or torsional moment square. Okay, now this equation which we have written, this equation can be rewrite as this tau max is equal to this, only this term we can take to the one side. Okay, under root m square plus t square. Okay, this term is equal to, here 16 divided by pi d cube is there, so it will become pi divided by 16 into tau max. Here is not the tau which we have calculated, into d cube. Now from this equation we can easily calculate value of d. Any question? So by means of applying this equation and this equation, we can calculate diameter of that shaft. Now if you want to calculate diameter, or if you want to design hollow shaft, what changes we have to make? Whether it will be D, or we have to change it from D. So if you want to use the same equation for hollow shaft, then what modification we have to make? I'll put on the next slide. For the hollow shaft, what we have to do, a T equivalent will become DO, which is mentioned as the outer diameter of the shaft, and DI as the inner diameter of the shaft. And this K is nothing but the ratio of outer diameter to inner diameter. So I will mention here, where D suffix O is outer diameter of shaft. Okay. And DI is inner diameter of shaft. Okay. And K is equal to DO by DI. Any question? Okay. When we are going to use this, we are going to use when maximum shear stress theory. Whereas when we are going to use maximum principal stress theory, in that case, this equation will become as ME is equal to 1/2 m square, sorry, m plus under root m square plus t square is equal to pi by 32 sigma b into do cube into bracket 1 minus k raised to 4. No, it will not k raised to 4. It will be k raised to 3. Equation चुकला है. Should be k raised to 3. Yes, sir. बरोबर आहे का? Hello?
Yes, sir.
It should be k raised to 3. Same way, at this place also it is k raised to 3. Hope you have understood. And we have completed this design of shaft by means of principal stress theory and torsional stress theory. Okay, we'll stop here. I'll take present T, and if time permits, today or tomorrow, I will finish this unit and next unit also. Hello? Can you listen me?
Yes, sir.
Okay. So I'll take present now.